The global refrigeration industry is worth $230 billion. The average American refrigerator runs 24 hours a day, 365 days a year, consuming roughly 500 kilowatt hours annually. That is $150 a year, every year, for the rest of your life, just to keep lettuce crisp and milk cold. And sitting on the shelf of any hardware store right now is a material that does the exact same job. It costs $3. It uses zero electricity. It has no compressor, no coolant, no moving parts, no monthly bill. It absorbs heat when temperatures rise and releases it when temperatures fall, automatically, passively, indefinitely. That material is paraffin wax. In 1971, NASA engineers at the Johnson Space Center in Houston needed a way to regulate temperature on the Skylab space station. There was no power budget for conventional refrigeration, so they sealed paraffin wax inside aluminum honeycomb panels and let phase-change thermodynamics do what no compressor in existence could do in zero gravity. It worked. It worked so well that NASA used it again on the International Space Station, and again on deep space payload missions. The research was published internally. The patents were filed. The thermal performance data was documented in NASA technical reports that most Americans have never seen and will never be told about, because the moment this science reaches your kitchen, a $230 billion industry loses its oldest and most reliable customer, your electric meter. Welcome to Nature Lost Vault. Today, we are opening the file on the fridge that does not plug in. To understand why a $3 block of wax can replace an $800 machine, you need to understand one principle: phase change. Every material on Earth exists in one of three states: solid, liquid, or gas. When a material transitions from one state to another, it absorbs or releases an enormous amount of energy. This energy is called latent heat, and latent heat is the single most powerful thermal tool in physics. Here is what that means in plain language. When ice melts into water, it absorbs heat from everything around it. That is why a glass of ice water stays cold. The ice is not creating cold, it is absorbing heat, and it absorbs a tremendous amount of it. 334 kilojoules per kilogram to be precise. That is enough energy to heat a kilogram of water from 0 to 80 degrees Celsius. All of it consumed silently during the phase transition from solid to liquid. Paraffin wax does the same thing. But unlike ice, it does not melt at 0 degrees. Different paraffin formulations melt at different temperatures. You can buy paraffin wax that melts at 4 degrees Celsius, that is 39 degrees Fahrenheit. That is refrigerator temperature. And when it melts at that temperature, it absorbs between 170 and 200 kilojoules of heat per kilogram from its surroundings. That means a single kilogram of paraffin wax, roughly $3 worth from any craft supply store, absorbs as much heat during its phase transition as it would take to raise a kilogram of water by nearly 50 degrees. That heat energy is pulled directly out of the air inside whatever container the wax is placed in. The temperature drops, the food stays cold. No compressor, no refrigerant gas, no electricity, just physics. And when the ambient temperature drops at night, the wax resolidifies, it releases the stored heat back into the environment, and the cycle resets. Every single day. Indefinitely, the wax is never consumed. It is never degraded. It simply oscillates between solid and liquid states, absorbing and releasing heat in a rhythm governed by nothing more than the temperature around it. This is what physicists call a passive thermal regulation system, and it is, by every measurable standard, the most energy-efficient method of temperature control ever documented. NASA did not invent this physics. The physics has existed since the beginning of the universe. What NASA did was prove that it works for thermal regulation in the most demanding environment ever conceived: outer space, where there is no air, no power grid, no margin for error, and where a temperature fluctuation of 10 degrees in the wrong direction can destroy a $400 million satellite. Their published research, available as NASA Technical Memorandum 20,110,010,960, and NASA Technical Paper 20,150,003,481 on the NASA Technical Reports server, documented that paraffin-based phase change material heat sinks maintained stable operating temperatures for electronic systems aboard the International Space Station for over a decade. Not with active cooling, not with fans or compressors, with wax. Let that sit for a moment. The same material that holds a candle wick upright kept a $150 billion space station thermally stable for years. And nobody told you it could keep your chicken from spoiling. But the truth is, humans figured this out long before NASA filed any reports. In 400 BC, more than 2,400 years ago, Persian engineers built structures called yakhls. The word translates directly from Farsi as ice pit. These were massive, domed buildings, some standing over 60 feet tall, constructed from a special mud brick mortar called saruj, a mixture of sand, clay, egg whites, lime, goat hair, and ash that was effectively waterproof and provided remarkable insulation. The yakhal worked in the middle of the Iranian desert, where summer temperatures exceeded 40 degrees Celsius. The Persians would channel water from mountain aqueducts into shallow pools adjacent to the yakhal during winter nights. The combination of radiative cooling, the process by which surfaces lose heat to the clear night sky, and the extreme dryness of the desert air would freeze the water. The ice was then cut into blocks and stored inside the yakhal's underground chamber. The thick mud walls, the domed shape that channeled hot air upward and away from the stored ice, and the underground design that tapped into the Earth's constant subsurface temperature created a system so efficient that ice remained frozen well into the hottest months of summer. Some yakhals stored up to 5,000 cubic meters of ice. In the desert, without electricity, without mechanical refrigeration, without any technology that a modern engineer would recognize as a cooling system, the Persians used these structures to store food, chill water, and make a frozen dessert called faluda that may be the oldest ice cream in human history. Over 100 yakhals have survived to the present day across Iran. Some are over 1,000 years old. They stand as physical proof that cold storage does not require a compressor, a refrigerant, or an electrical outlet. It requires an understanding of how materials absorb and release heat, an understanding that an ancient civilization possessed 2,400 years before General Electric sold its first refrigerator. And then there is the version from Africa. In 1995, in the Jigawa state of northern Nigeria, a schoolteacher named Mohammed Ba Abba was watching his community lose nearly half its food to spoilage. There was no electricity grid for hundreds of miles. There was no refrigeration. In a region where summer temperatures regularly exceed 40 degrees Celsius, fresh produce lasted no more than 2 to 3 days after harvest. Mohammed came from a family of potters. He understood clay, and he understood what happened when water evaporated through a porous surface. He took a small clay pot and placed it inside a larger one. He filled the gap between the two pots with wet sand. He placed food inside the inner pot and covered it with a damp cloth. As water seeped through the porous outer pot and evaporated into the dry desert air, it pulled heat energy away from the inner chamber. The temperature inside dropped to as low as 6 degrees Celsius. In the middle of the Nigerian desert, with no electricity, no moving parts, no technology that cost more than the equivalent of 40 cents. The results were documented. Tomatoes that spoiled within 2 days at ambient temperature lasted 21 days in the pot-and-pot cooler. Peppers lasted over 3 weeks. Eggplant that would have rotted overnight remained fresh for nearly 2 weeks. Fresh meat could be stored safely for days rather than hours. Mohammed called it the Zir pot, with the help of a $75,000 Rolex award for enterprise that he received in the year 2000. He distributed nearly 100,000 Zir pots across 11 northern Nigerian states. Childhood malnutrition rates dropped in communities that adopted the system. Girls who had previously been kept out of school to sell produce before it rotted could attend class because the food no longer spoiled. The Zir pot was adopted in Eritrea to store insulin for diabetic patients in remote areas. It spread to India, Haiti, and Honduras. Time magazine named it one of the best inventions of 2001. Mohammed Ba Abba passed away in 2010. He was 46 years old. Outside of development circles, almost no one in the Western world has ever heard his name. A man saved thousands of lives with 2 clay pots and wet sand. And the refrigeration industry, worth $230 billion, did not mention him once. Now let us bring this story into the present. NASA's research on paraffin-based phase change thermal regulation is not classified in the traditional sense. The technical reports are publicly available on the NASA Technical Reports server. Anyone can read them. The physics is not secret. The materials are not restricted. But there is a difference between information being publicly available and information being publicly known. And the gap between those two things is where entire industries build their revenue models. The global home appliance market generates over $600 billion annually. Refrigerators alone account for the largest single share of household electricity consumption. In the United States, residential refrigeration uses approximately 7% of all household electricity. The Department of Energy estimates that American households collectively spend over $18 billion per year just running refrigerators and freezers. That is $18 billion in electrical revenue that flows through utility meters, is billed by power companies, and represents a foundational revenue stream for the electrical grid. Now imagine if 10% of American households switched to passive phase change cooling for even part of their cold storage needs. That is $1.8 billion in electricity revenue that disappears, not shifted, not replaced, simply gone. Because a block of wax does not draw current, the appliance manufacturers know about phase change materials. PCM technology is already used in commercial cold chain logistics, in pharmaceutical shipping, in military field operations, and in European building insulation. The thermal engineering departments at Whirlpool, Samsung, LG, and GE all employ materials scientists who are intimately familiar with paraffin wax as a thermal storage medium. This is not obscure science. It is taught in undergraduate thermodynamics courses. But here is the economic reality. A conventional refrigerator is a subscription product. It costs $800 to $2,000 to purchase. It costs $100 to $200 per year to operate. Its compressor, the most expensive component, has an average failure rate that requires $300 to $1,250 in repairs. Consumer Reports estimates that 33% of all refrigerators require repair by the end of their 5th year. And the average lifespan is 10 to 14 years, at which point the consumer purchases another one. That is a business model that generates revenue at every stage: purchase, operation, repair, replacement. For revenue events across a 10 to 14-year cycle, then the cycle starts again. A paraffin wax cooler generates one revenue event. $3 once, then it works forever. There is no commercial incentive to produce it. There is no advertising budget for it. There is no retail shelf space allocated for it. There is no industry lobby advocating for its adoption. And there is certainly no major appliance brand that will voluntarily cannibalize its most reliable revenue stream by telling you that a block of wax does what their flagship product does for 1/1000th of the price. This is not a conspiracy. It is economics. It is the same economics that kept the electric car suppressed for decades, that kept generic pharmaceuticals out of markets for years, that keeps repairable devices off the shelves in favor of disposable ones. When a cheap solution threatens an expensive one, the expensive one does not disappear. It simply outspends the cheap one in marketing. Here is how you build a wax fridge. Today, for under $5, you need 4 things: a rigid, insulated container, paraffin, wax with a melting point between 2 and 8 degrees Celsius, sealable plastic bags or thin plastic containers, and aluminum foil. The container can be a standard styrofoam cooler from any gas station or hardware store, the kind that costs $2 to $5, or an old cooler you already own, or a wooden box lined with rigid foam insulation boards from any home improvement store. The key specification is insulation. The better insulated the container, the longer the wax can maintain the internal temperature. A cheap styrofoam cooler will give you 24 to 48 hours. A well-insulated wooden box with 2-inch foam panels will give you 72 hours or more. The paraffin wax is available from candle-making suppliers, craft stores, and online retailers. You need food-grade paraffin wax or a specific PCM paraffin blend with a melting point in the refrigeration range. A single pound of paraffin wax costs between $2 and $5. For a small cooler, you need approximately 1 to 2 pounds. For a larger unit the size of a standard mini fridge, 3 to 5 pounds. Here is the assembly process. Take your paraffin wax and melt it in a double boiler on the stove. Do not heat paraffin over direct flame. It is flammable at high temperatures. A double boiler keeps the temperature controlled and safe. Once the wax is fully liquid, pour it into sealable plastic bags or thin plastic containers. Flat, rectangular shapes work best because they maximize surface area, which maximizes the rate of heat exchange. Seal the containers. Allow the wax to cool and solidify at room temperature. You now have wax packs. Place the wax packs in your freezer for 12 hours before first use. This brings the wax well below its melting point, giving you maximum thermal storage capacity for the first cycle. Line the inside of your insulated container with aluminum foil. The foil acts as a radiant heat barrier, reflecting infrared radiation away from the stored food and back toward the walls. This is the same principle used in emergency space blankets and NASA thermal shielding. Place the frozen wax packs along the bottom and sides of the container. Place your food in the center. Close the lid. Here is what happens. The ambient heat outside the container slowly penetrates the insulation and enters the interior airspace. When that heat reaches the wax packs, the wax begins to melt. As it melts, it absorbs between 170 and 200 kilojoules of thermal energy per kilogram of wax. This absorption pulls heat out of the interior air, dropping the temperature as long as the wax is in the process of melting. The interior temperature remains stable at the wax's melting point, which, if you selected the correct paraffin formulation, is between 2 and 8 degrees Celsius. Refrigerator temperature? This process continues for as long as the wax has unmolten mass remaining. In a well-insulated container with 2 kilograms of paraffin, that is 24 to 72 hours, depending on ambient conditions and how frequently the container is opened. When the wax is fully melted, the cooling cycle is complete. To reset the system, place the wax packs back in a freezer, a cold stream, or simply leave them outside overnight in any climate where nighttime temperatures drop below the wax's solidification point. The wax resolidifies, the thermal energy is released into the environment, and the cycle is ready to begin again. No electricity consumed during the cooling cycle. None. The only energy input is the initial freeze, which can be accomplished by any cold source, natural or mechanical. And in many climates, nighttime temperatures are sufficient to reset the wax without any artificial cooling at all. For long-term off-grid use, you can build a larger version using a well-insulated chest with 5 to 10 kilograms of paraffin and a nighttime reset system that simply places the wax packs outside between sunset and sunrise. In a climate with diurnal temperature swings of 15 degrees or more, which covers most of the continental United States for most of the year, this system is self-sustaining. It cools during the day. It resets at night, indefinitely. Here is the math the industry never wants you to see on the same page. A conventional refrigerator. Purchase price, $800 to $2,000. Annual electricity, $100 to $200. Repair cost over lifetime, $300 to $1,250. Lifespan, 10 to 14 years. Total cost of ownership, $2,000 to $5,000. Uses refrigerant gas that is a potent greenhouse gas if leaked. Requires continuous electrical connection. Ceases to function immediately during a power outage. A paraffin wax cooler, construction cost $3 to $10 in materials. Annual electricity $0. Repair cost $0 because there are no mechanical parts to fail. Lifespan indefinite because wax does not degrade through thermal cycling. Total cost of ownership $3 to $10. Uses no requires no electrical connection. Continues to function during any power outage, any grid failure, any natural disaster. Over a 50-year adult life, the refrigerator path costs a household between $10,000 and $25,000 in purchase, electricity, and repairs across multiple units. The wax cooler path costs less than a meal at a fast food restaurant once, and the food stays cold either way. This is not a theoretical comparison. This is published physics and published economics on the same page. The only reason these numbers have never appeared in the same advertisement is that no one profits from the second column. For those who want to take this further, the science scales. European building engineers are already embedding micro-encapsulated paraffin wax into drywall panels and concrete walls. When the indoor temperature rises above a set threshold, the wax melts inside the wall, absorbing heat and preventing the room from warming further. When the temperature drops at night, the wax resolidifies and the cycle resets. Published studies show that PCM integrated building walls can reduce cooling energy consumption by 20 to 40%. The technology is commercially available in Europe. It is barely mentioned in the American construction industry. The military has used PCM cold packs for decades to maintain vaccine cold chain integrity during field deployments. The pharmaceutical industry ships billions of dollars of temperature-sensitive medications in PCM containers. The technology is trusted to protect human lives when conventional refrigeration is unavailable. But it has never been marketed to the one customer who would benefit from it the most, you. And here is the most remarkable application. Study published in Applied Sciences tested a phase-change material cold storage container against conventional insulated shipping coolers. The PCM container maintained internal temperatures between 4 and 5 degrees Celsius for over 80 hours, not 24 hours, not 48 hours, 80 hours, more than 3 full days. With zero electricity, the control cooler, using conventional ice packs, failed within 12 hours. 80 hours of refrigeration from a material that costs $3 a pound and never needs to be replaced. The science is published. The study is peer-reviewed. The data is irrefutable. Let us put this vault into perspective. 2,400 years ago, the Persians built ice houses in the desert using mud and physics. They stored 5,000 cubic meters of ice in 40-degree heat without a single mechanical component. In 1995, a Nigerian schoolteacher kept tomatoes fresh for 21 days in the Sahel Desert using 2 clay pots and wet sand. He saved thousands of lives. He died at 46. The world forgot his name. In 1973, NASA engineers sealed paraffin wax inside aluminum panels and solved thermal regulation for the most advanced machines humanity has ever built. The data was published. The technology was proven. It was never brought to your kitchen. The Persian Yakchul, Mohammed Ba, Abazir pot, NASA's phase-change heatsink, 3 solutions separated by 2,400 years of history from 3 different corners of the Earth, all of them based on the same fundamental physics. A material changes state. Heat is absorbed, temperature drops, no electricity required. And all 3 of them were either forgotten, ignored, or kept from the one place they were needed most, your home, not because they did not work. They all worked. But because a solution that costs $3 and lasts forever does not sustain a $230 billion industry that depends on you paying $150 every year for the privilege of plugging into a wall. The science is published, the history is documented, the materials are on the shelf of your nearest hardware store. The only thing standing between you and a fridge that never needs power is the knowledge that was kept from you until now. If this vault opened something for you, subscribe to this channel and hit the bell. Every like, every share preserves what they try to erase. The next vault opens soon.